the lab demonstrations of communication systems lab course. Now this demonstration that we're going to do here is aimed at enabling you to understand the concepts, the underlying concepts of communication in a better manner, combining this with whatever you have learned in the classroom, combine these two things and understand the subject in a better way. So in this demonstration, we are going to use, throughout these demonstrations, we are going to use two instruments very widely. One is the oscilloscope, which all of you are familiar with. I have two oscilloscopes here. One is the AppLab oscilloscope, the other is Agilent oscilloscope. Okay? And today we will introduce you to another instrument which is very important for a communication engineer. This instrument is called as a spectrum analyzer, which is this one. Okay, so we will combine both these instruments, the oscilloscope and spectrum analyzer, in understanding various concepts of communication signals that you will study in your class. We will also see those signals in practice in this lab, in this demonstration. Okay, so now let us first talk about the instrument that you are familiar with, that is the oscilloscope, which is also called as cathode ray oscilloscope. We normally call it as oscilloscope. Now let us look at the oscilloscope that is kept here. The screen of the oscilloscope will give you voltage or amplitude versus time. So when I represent the signal on an oscilloscope, I say that I am presenting the signal in its time domain. That is, I am looking at a time domain picture of the signal. How will I feed the signal in? I have these two BNC connectors here and here. I will feed the signal through a BNC cable to this input or to this input or to both of them. This is called a dual trace oscilloscope. It's got two traces. So I can represent two signals at the same time by feeding one signal each to each of these BNC inputs. Now this oscilloscope on top is mentioned 30 megahertz. What does this tell me? This tells me that this oscilloscope is capable of measuring signals up to 30 megahertz frequency. If I have a signal which is having a frequency larger than 30 megahertz, I will not be able to represent that signal on this oscilloscope. I have to go for a better model. Now this oscilloscope is a cheap one, which costs about 20,000 rupees or so. There are more expensive oscilloscopes available in market which can cost you up to a lakh or so. Now on the front screen, as I said, this x-axis is the time axis. On this vertical axis is the amplitude or voltage axis. I can scale these axes, the horizontal axis as well as the vertical axis, by changing these settings. The vertical axis can be changed by this switch, the horizontal axis can be changed by this switch. Now this switch on top is mentioned volts per division. That is, I can change the number of volts. Looking at the number of divisions here, I can change the scale of vertical axis. I can likewise change the scale of horizontal axis using this knob. Okay, so this way I can represent the signal. I can display a signal in a very convenient form, and I can extract various parameters from that signal. It is usual, if you have a periodic signal, to measure its time on the x-axis and then invert that time to get the frequency of the signal, and that's how all of us have measured in the earlier experiences. Now this is also an oscilloscope, but this is called as a digital storage oscilloscope. That is a simple analog oscilloscope. This is a digital storage oscilloscope. Now how is this oscilloscope different from this oscilloscope? Both oscilloscopes display the signal in time domain. The only difference between this oscilloscope, the only way this oscilloscope is different from this oscilloscope is this oscilloscope will display the signal in real time, whereas this is displaying a reconstructed signal. Now why is it reconstructed? This is a digital oscilloscope. So at first, when you input an analog signal to the digital oscilloscope, it will first sample it, quantize it and reconstruct it. So what you see on the screen is not a signal in real time, it is reconstructed signal. Okay? On the other, and this, it is possible for me to store the signal in a digital format. It can give me a .bitmap file, it can give me a JPEG file. So I can store these signals, the display, in various digital formats. I can use that on my computer for my presentations and other things. There's a small floppy drive here. I can use a small 3.5-inch floppy in this and store the signals in whichever format I want. Okay? So this is why this is called as a digital storage oscilloscope. On the top of the oscilloscope, it is also mentioned mixed signal oscilloscope. Now what does this mixed signal oscilloscope mean? You look at the inputs to the oscilloscope, there are two analog inputs. There are channel 1 and channel 2. If I have an analog signal, I can feed an analog signal to these two inputs. Apart from this, I have 16 digital channels which are located here. Now where are these useful? Suppose I want to represent signals coming out of a microprocessor or a computer. Okay? What I'll do is I'll simply connect the pins of microprocessor output, the output of microprocessor, I'll simply connect to the digital channels here. So I can directly display digital signals on the screen. I can also display analog signals on the screen. Since I can display both digital signals as well as analog signals, this is called as a mixed signal oscilloscope. Again, on the top of this oscilloscope, it is 60 MHz written here. This tells me that I can represent signals up to a frequency of 60 MHz. If a signal has a frequency larger than 60 MHz, I will not be able to present that signal on this oscilloscope. I'll have to go for another oscilloscope. Below that 60 MHz, you see 200 megasymbols per second written. Remember, in the beginning I told you that this samples an analog signal, quantizes it and represents it in a binary form, in a digital form. So this is a sampling rate, which is this 200 megasymbols per second. So I am sampling an analog signal at the rate of 200 megasymbols per second and representing this in a digital format. Okay, so this is why this is called as a digital storage oscilloscope. That's an analog oscilloscope. Now, this instrument is called as a spectrum analyzer. Now, let us understand what is meant by the word spectrum. When I measure a quantity, when I say that I am measuring a quantity as a function of its frequency or a function of wavelength, I say that I am measuring the spectrum of that quantity. Okay, that quantity can be anything. It can be X, it can be Y, it can be Z, whatever be that quantity. As long as it's a function of frequency or wavelength, I say that I am recording the spectrum of that quantity. Okay. Now, just like you had an oscilloscope where you had a vertical axis as the voltage axis and horizontal axis as the time axis, on a spectrum analyzer, the vertical axis is the power axis, the horizontal axis is the frequency axis. Now let's go back to the classroom and we understand what are we meaning by this. Suppose I have a signal which is represented in time domain by small x in brackets t. Okay, that is x as a function of time. Supposing I am interested in the spectral content of the signal. What will I do? I'll actually mathematically calculate the Fourier transform of this. If I calculate the Fourier transform is a tool which takes me from time domain to frequency domain. So I multiply x t by e power j omega t dt, integrate over minus infinity to plus infinity, gives me x of omega. That x of omega is what is being represented by the spectrum analyzer. So x of omega is nothing but the spectrum of x of t, the spectral content of x of t. That is what we are interested in. Now, why are we interested in frequency domain representation in communication? You must understand that in communication system, I will have a transmitter, I will have a receiver, and I will have a physical medium that connects the transmitter to the receiver. Now, this physical medium could be in the form of twisted copper wire, like in the case of landline phones. It could be a fiber optic cable, as in the case of optical communication. It could be even free space, as in the case of mobile communication or satellite communication. So we call this physical medium through which the signal travels as a channel. So a channel is a region which connects the transmitter to the receiver. Now when a transmitter inputs a signal to the channel, a receiver extracts the signal from the channel and demodulates it. Okay? Now what can happen is, when a signal propagates through the channel, the signal can get distorted. What do I mean by saying that signal can get distorted? If you see, if I calculate the Fourier transform of a signal, I am representing the signal in frequency domain as capital X of omega. I can write this capital X of omega as equal to modulus of X of omega multiplied by a phase factor. Now when I say the signal is getting distorted, the amplitude can get distorted, that is the magnitude can change or the phase can change. Okay? Now if the magnitude has got distorted, I say the signal has suffered distortion in amplitude. If the phase has got distorted, I say the signal has suffered distortion in phase. It is possible that a signal can get distorted in amplitude only, or in phase only, or in both amplitude and phase. So when both amplitude and phase are distorted, the input signal which was input into the channel will not look the same as the signal that was output from the channel. So when the input signal is not same as the output signal, obviously the signal has suffered distortion. Okay. So in communication, we want this distortion to be as minimum as possible. So we would like to have some idea about the spectral content of our signal before we transmit it on a channel. Okay, the channel can modify the spectral contents and therefore distort the signal altogether. So it is very important for us to know the spectral content, which is why we would like to analyze the channel. We'd like to analyze the signal on a spectrum analyzer. We'd like to see its spectral content. Okay. Now, as I said, on this spectrum analyzer, the horizontal axis denotes the frequency and the vertical axis denotes the power. Now the power on this spectrum analyzer can be represented in linear scale. It can also be represented in logarithmic scale. Now why is logarithmic scale important? Often in communication you will find that power is often represented in a logarithmic scale. The reason being that when a signal travels from a transmitter to the receiver through the communication medium or the channel, the signal can change power over a large scale. That is, if I am having, let's say for example, if I am talking about milliwatt, let's say if I am talking about few watts of power being transmitted by the transmitter, and let's say that at the receiver I am receiving microwatts of power. When I am transmitting 1 watt of power, I am receiving 1 microwatt of power at the receiver. The power has changed by 6 orders of magnitude. On a linear scale, if I were to represent this 6 order of magnitude of power change, it will be very difficult for me. But on a logarithmic scale, it's easy for me to represent powers because the power can change over large value. Secondly, wherever I need to divide or multiply the power, I can simply subtract or add in decibel scale. So multiplication in linear scale is equal to addition in logarithmic scale. Division in linear scale is equal to subtraction in logarithmic scale. So it's very easy for us to add and subtract rather than multiply and divide the signals. So this is the reason why we would like to use logarithmic scale rather than linear scale. So on this spectrum analyzer, you see there are rectangles. Now this is basically a grid. Okay, each rectangle on the vertical axis represents 10 dB of relative power. Now you should be very comfortable with the dB scale. When I talk about absolute power, I will talk in terms of dB watts or dB milliwatts or dB microwatts and so on. Accordingly, we designate them as dBW, dBm and dB micro, dB mu. Okay. Now, when I am talking about absolute power, that is, I am looking at a particular frequency component, how much power it has got. I will say that this frequency has got so many dBm of power. But when I am looking at two different frequencies on the same spectrum, I will say that these two frequencies are differing by so many dB of power. I am talking about relative difference between the power level here and the power level here. Obviously the power content, let's say if we are talking about 2 points in the spectrum, this point obviously has got more power than this point. So I would say that this point is so many dB above this point, or I will say this point is so many dB below this point. So it's always, when I am talking about relative power, I will talk in terms of dB. When I talk about absolute power, I will talk in terms of dBm. In this kind of communication system, we normally talk in terms of dBm of power. Okay. So this is, each rectangle here represents 10 dB of relative power. On the horizontal axis is the frequency. How do I set the frequency? I make use of this switch here. Okay. So this switch, if I press, let's press the switch. You see this display changes to whatever is corresponding to this menu. Okay. Now there is a start frequency, there is a stop frequency, and there is a center frequency. Now what is the start frequency, what is the stop frequency? Start frequency defines the beginning of my scan, stop frequency defines the end of my scan. Okay. So I want to scan in a certain range, I can enter the start frequency and stop frequency. Alternatively, I can define a center frequency and define a span. I can have a center frequency and define a span, how much around the center frequency I want to measure. Okay. So I can do that. So I can have frequency. Notice this button, this is called as, this is the one I will use to set the span. Okay. So I can do either of this. I can either have start frequency and stop frequency separately input, or I can have center frequency defined and also define a span. The next is amplitude. Like I told you in an oscilloscope, I can also change the y-axis scale, I can change the amplitude to display the signals in a proper manner. Okay? Now how do I connect the signal to the oscilloscope, to the spectrum analyzer? This is the input. This is the input to the spectrum analyzer. So to this input, I will connect what is called as a BNC cable. Now there are BNC cables. You might have used this kind of cable very frequently in your lab. This is called as the BNC cable. BNC stands for Bayonet, Neal, Conselman. Okay? Neal and Conselman were two scientists who invented this cable. Bayonet is an arrangement, a locking arrangement. You see this connector. If you put this connector into an oscilloscope or into a spectrum analyzer, there is a mechanism by which you can lock this connector. This is called as a bayonet. Okay? And so this is called as a Bayonet, Neal, Conselman, BNC cable and BNC connector. Now, why is BNC connector so important? If you see this front side of the BNC connector, you see a tiny pin-like thing at the center. Now that pin is the one which is carrying the signal. Now if the signal were exposed to the surroundings, you might have electromagnetic interference. Okay? To protect the signal from any kind of interference, there is a protective sheath, a conducting sheath around it, and that is the ground. Okay? So the center pin is signal, surrounding one is the ground. So if you see a BNC cable, you will have the center pin as the one which is carrying carrying the signal, and this is the ground, which is the surrounding conducting sheath. Okay? So this conducting sheath protects the inner conductor from the signal in the inner conductor from getting interfered with other signals, RF interference. So I'll simply connect this to the input of the spectrum analyzer, and whatever signal this cable is carrying can be analyzed for its spectral content. It is very important for us to analyze the signals, at least in communication, for its spectral content. Before we proceed further, let me just mention about one more important thing. When we have this BNC connector here, you notice next to it is written input 50 ohms. Now what does this input 50 ohms mean? This means I should connect a cable which has got an impedance of 50 ohms to this connector, because there has to be an impedance matching between the cable and this connector. What will happen if there is impedance mismatch? Now if you go back to your ES1 concept, all of you have studied something called as maximum power transfer theorem. That is, there has to be a matching between the load and source in order for maximum power to transfer from the source to the load. So in this case, if there is no matching of impedance between the cable and the connector, a large amount of power might reflect back. So what power you are measuring, your instrument is measuring, may not be the true power that the cable is carrying, it may be only the transmitted power. So for the reflections to become minimal, it is important for us to have impedance matching. So that is why I cannot connect an arbitrary cable to this input. I must connect a cable having a 50 ohm impedance to this input. Likewise, if you have a video signal, you will have a 75 ohm input impedance cable. So you will have to connect only that kind of cable to this input. Okay? I cannot arbitrarily connect any kind of cable to this input. You can still display the signal, but the power content of the signal will not be same as that in the power content that is displayed on the screen will not be same as that which is being carried by the signal. Okay, so that is very important. Now, you have similar thing for the oscilloscope also. All these things are listed here in the front panel of the instrument. There's another important thing to do with this is that you should worry about how much maximum power can I put in. Now there is obviously a limit. Now this instrument can take maximum of 1 watt plus 30 dBm, 1 watt maximum power. If I put in power more than 1 watt, this instrument is likely to get damaged. Okay, so it is important that we pay attention to all these factors before we begin to use the instrument. The instrument comes with, any kind of instrument will come with manufacturer's manuals, and this is very important for you to consult the manual before you start using the instrument, because there are a number of do's and don'ts which are listed by the manufacturer so that the instrument can be operated safely. So you cannot input power more than 1 watt to this instrument, and you respect all those conditions set by the manufacturer. Now there are important things about spectrum analyzer. For example, the range of operation. The second thing that is important about spectrum analyzer is dynamic range. Now dynamic range is the ability of the instrument to display a weak and a strong signal at the same time. So when I have a weak signal and a strong signal present at the input of the spectrum analyzer at the same time, the spectrum analyzer should be able to display both the signals at the same time. So dynamic range is the difference in the power level between the strong signal and the weak signal. And remember, it's a relative difference, so I'm talking in terms of dB. So typical dynamic range of spectrum analyzers is about minus 90 dB or so. The second thing that is important is the sensitivity. The sensitivity is the smallest amount of power that the instrument can reliably measure. And the sensitivity is always measured at the minimum resolution bandwidth. I'll tell you what resolution bandwidth is. So the sensitivity is very important because when I'm dealing with very tiny powers, the instrument should be able to measure those powers and display those powers. So sensitivity is another important factor of a spectrum analyzer. The third important factor of a spectrum analyzer is the resolution bandwidth. Now what do I mean by resolution bandwidth? First, to understand this, let us understand what is meant by the principle of heterodyny. I have a small diagram here. You see, here is F in, that is the input signal, and this is a local oscillator which is present inside the system. This cross, a circle with a cross, is the mixer. So I input the input signal and the local oscillator signal into the mixer. I generate, now this mixer is a nonlinear device. If I have a nonlinear device, I can add or subtract frequencies. So at the output of this nonlinear device, I will have sum of the frequencies, I will have difference of the frequencies. Fin minus FLO, that is the difference between this frequency and this frequency, is what we call as the intermediate frequency, which I designate by FIF. Now this intermediate frequency goes into an intermediate frequency amplifier followed by an intermediate frequency filter. Now remember that this is a nonlinear device, it can also generate unwanted products. So it is important for me to filter out those unwanted products. I pass this intermediate frequency signal through an intermediate frequency filter. I can tune this filter, I can change its bandwidth. So when I talk about resolution bandwidth, I am essentially talking about the bandwidth of this filter. Okay, so I can change the bandwidth of this filter in steps of 1:3:10. That is, the minimum is 1 kilohertz. So the minimum resolution bandwidth is 1 kilohertz. Next is 3 kilohertz. Next is 10 kilohertz. Next is 30 kilohertz, 100 kilohertz, 300 kilohertz, and so on. So I can go in steps of 1:3:10. So that's the way I can change resolution bandwidth. So sensitivity of the instrument is measured at the minimum resolution bandwidth, the tiniest, the smallest power that the instrument can measure at the smallest resolution bandwidth available in the instrument. So these are the three important specifications of the instrument you must keep in mind if you want to order a spectrum analyzer or if you want to work with a spectrum analyzer. Okay, so these are some of the things you need to keep in mind when we go with the demonstrations further. So next demonstration, I am going to show you how we characterize filters in lab using a spectrum analyzer. Now before this, let us quickly recollect how we traditionally measure the filter characteristics in lab. To measure the filter characteristics traditionally in the lab, I will require, of course, the filter circuit, I will require an oscilloscope, and I will require a function generator. So how is the experiment done here? Each time I will feed in a particular frequency with a particular amplitude, a signal with a particular amplitude and particular frequency, and I will measure the same signal at the output of the filter, note its amplitude. I will keep on repeating this for every frequency, I will keep noting the output, and I will make a tabular column of input frequency and amplitude at the output. So then I plot a graph between the amplitude ratio, amplitude output divided by amplitude input versus the frequency. And then I will have a plot which gives me the frequency response of the filter. That's the traditional way we do the filter characteristics. Now in industry, people do not have so much of time to sit and measure every data point and take readings. The simplest way I can characterize a filter is to simply use a spectrum analyzer and characterize it. So the next demonstration will be about that. In the previous demonstration, we introduced ourselves to oscilloscope and to spectrum analyzer. Today, we will try to see how filters are characterized in practice using a spectrum analyzer. Now let us go back to the spectrum analyzer. Now this is the instrument that we had talked about in the previous demonstration. Now there are two connectors here. Now this already I have mentioned is the output, that is the one which is carrying the signal to the spectrum analyzer. So this is the input to the spectrum analyzer. There is another similar output available from the spectrum analyzer. Now this output carries a broad set of frequencies from 9 kHz to 1.5 GHz. This spectrum analyzer has got a broadband source inside which can generate frequencies from 9 kHz to 1.5 GHz. So now instead of using a function generator and then inputting individual frequencies to the filter, I would present all these frequencies at the same time to the input of the filter. The filter would respond to these frequencies. The output is the filter response which is collected by this cable and then fed into the spectrum analyzer. So this is a small filter kit we have got. Now this filter kit here, this is a low pass section, this is a band pass section, this is a band reject section. So I can make low pass filters, I can make band pass filters, band reject filters, and you people will be doing that, the similar experiment using Butterworth second order filters. Okay, you can make a Butterworth filter, second order Butterworth low pass filter, high pass filter, band pass filter and band reject filter, just what your first hardware experiment is. So assuming that I have a filter of that kind, how do I characterize the filter? That's the question we are trying to ask. So here what we will do is, we are inputting broad set of frequencies from 9 kHz to 1.5 GHz at the same time to the input of the filter. The frequencies are present here. The filter responds to these frequencies. I am taking the response of the filter and then feeding it to the spectrum analyzer. So what you should observe is now this filter is configured as a low pass filter, and the typical characteristic of a low pass filter is what is shown on the spectrum analyzer. Now this is typically the trace of a low pass filter, the way to respond to the frequencies. Now there are certain set of frequencies which are passing unattenuated, and above particular frequency there is a gradual attenuation, and the attenuation is more severe at higher frequencies, which is what a low pass filter is expected to do. Now in the previous demonstration I told you about a marker. Look at this small dot here on the screen. This dot gives me the x-axis and the y-axis. That is, at a frequency of 510 kHz, there is a power of minus 20.85 dBm available. Okay. So now what is the important characteristic of filter? This is called as a roll-off. We measure roll-off as so many dB of attenuation per hertz of frequency. So this is the roll-off of the filter. It tells us how rapidly the filter cuts off unwanted frequencies, and the frequencies below this are unattenuated, passing through the filter. Frequencies above this cutoff frequency are the ones which are passing with severe attenuation. So cutoff frequency is a very important term of a filter, and we will show you how do I find this cutoff frequency on a spectrum analyzer. Now let us move this marker. I can move this marker by using this dial. Okay. Now let us note the power. It's about 15.97 dBm. Now cutoff frequency of a filter is defined in several ways. The traditional way is to define the 3 dB cutoff frequency. Now what is meant by 3 dB cutoff frequency? 3 dB cutoff frequency means it is that frequency at which the power through the filter falls by 3 dB compared to its DC value. That is, the power from DC value up to a certain value is almost constant. So that is what is about minus 15.97 dB. If this were to fall by 3 dB, then I would read minus 18.97 dB. Corresponding frequency is the 3 dB cutoff frequency of the filter. So let us move this marker now. So it is minus 15.97 dBm. I need to go to minus 18.97 dBm. That's where we are. So minus 18.97 dB. Corresponding frequency is 441 kHz. So this filter has a 3 dB cutoff frequency of 441 kHz. It is so simple compared to the way you would do using an oscilloscope and a function generator. You would have done similar experiment, it would have taken a much longer time. But here in one shot I am able to get the 3 dB cutoff frequency of a filter. So this is how I characterize a low pass filter. Now let us change this configuration to a high pass filter and see how a response of high pass filter should look like. So now what has happened? I have configured the filter to pass higher frequencies and cut off lower frequencies. This is why it is called a high pass filter. Low pass filter will pass low frequencies, cut off higher frequencies. High pass filter will pass high frequencies, cut off low frequencies. So all frequencies lying to the higher side are being passed by the filter. All the frequencies which are to the lower side have been cut off. Okay. Likewise, you see the power here is almost constant. So I can pick up any such point and then come 3 dB down. I note the power at this point, come 3 dB down, the corresponding frequency is the cutoff frequency. Now this is roughly, let's say right now 441 kilohertz minus 26.04 dBm. So if I come 3 dB down, I must come to minus 29.04 dBm. Okay. So let's move this marker. So this is minus 194 kilohertz. So that means this high pass filter has got a 3 dB cutoff of minus 194 kilohertz. That is, all frequencies above 194 kilohertz will be passing unattenuated through the filter. All the frequency components below 194 kilohertz are going to get severely attenuated. So this is how we characterize a high pass filter. So we characterize a low pass filter. Now we have characterized a high pass filter. The other kind of filters are band pass filter and band reject filter. Now let us see how the frequency response of a band pass filter look like, how the frequency response of a band reject filter look like. Now one thing that you must notice is when I talk about low pass filter or high pass filter, I had a single cutoff frequency. When I talk about a band pass filter and band reject filter, I will have two cutoff frequencies, one for the higher frequency and one for the lower frequency. So we will see that. Now what you are seeing on the screen is typically the frequency response of a band pass filter. Now how do I find the bandwidth of this filter? I will have to go to the peak frequency, note the power there, come 3 dB down on either side. Note the corresponding frequencies. The difference between these two frequencies is the bandwidth of the filter, is the 3 dB bandwidth of the filter. Okay? So all frequency components within that 3 dB bandwidth will pass unattenuated, whereas all other frequency components, look at the way it is cutting off the unwanted frequencies. The cutoff is very sharp. That is what is expected of a band pass filter. So now let us go to the peak. So let us say it's minus 19.66 dBm. If I come 3 dB down on either side, I must read minus 22.66 dBm on either side. I should note the corresponding frequencies, and the difference between those two frequencies is the 3 dB bandwidth of this filter. So let us go on this side. I should read minus 22.66 dBm. Okay, doesn't matter. We are at minus 22.83 dBm. So the power is the frequency is 493 kilohertz. So let's come to the other side. Okay, roughly minus 22.90, so this is 446 kilohertz. So the previous frequency, the higher frequency minus the lower frequency, is the 3 dB bandwidth of this band pass filter. So all the frequency components lying within this bandwidth will pass unattenuated. So notice that in high pass filter and low pass filter I had only one cutoff frequency. For a band pass filter I must specify both the cutoff frequencies and specify the bandwidth of the filter. Okay, so this is very important. Next we will see the configuration of a band reject filter. So now what you are seeing on the screen is the typical characteristic of a band reject filter. Now this is a very narrow band filter. It is rejecting a very narrow band of frequencies. Now these kind of filters, low pass filter, high pass filter, band pass filter, band reject filter, are all required in signal processing. So communication is a part of signal processing. So we use these kind of filters very frequently in signal processing. Likewise, I can also find out the 3 dB bandwidth of a band reject filter also. So all this is a simple way of characterizing filters, and in industry, in a real-time environment, this is the way people will characterize. Nobody would do an oscilloscope and a function generator. That is fine for laboratory, for understanding purpose. But in an industrial environment, this is the way you will characterize a filter. So this is the way we will characterize a filter using a spectrum analyzer. To characterize a filter using a spectrum analyzer, you will need a spectrum analyzer which has got a built-in source which can give you broad band of frequencies. You input those frequencies to a given filter, and then connect the output of the spectrum, the input of the spectrum analyzer to the output of the filter. And on screen you will be able to record the frequency response of the filter, and from there find out various parameters of the filter.